I'm just saying.
Oh, I was the hour lecture. I was. It's complicated.
All right, so I had something set wrong on that quiz, so it looks like it's out of 12 points. I changed it, but I don't know if the grade's updated, so I have to go in and manually do that this afternoon. That's why I haven't moved it down to kind of factor into your grade. So that'll be done sometime this afternoon. I'll throw that down there. It's those Excel. I'm hoping to do that this afternoon, so those should be graded. Those grades should start popping up this afternoon. Got that current connect assignment that's out there. And like I said, if you want to kind of read on what we're going to start covering on Monday, you can go ahead and kind of look through that. We'll kind of basically from next Monday to the end of the semester, just be doing regression analysis. Yeah.
Are those like?
They're not for points.
Okay.
No. So I can't make them show 0 points, but if you notice, I moved them down here into this category where it's 0%, right? So you don't have to do them if you want to kind of prime yourself for that, but they'll be out there. Okay. So that's where we're at with that. Like, there we go. So why can't I see this? So we've been doing this two population stuff and kind of doing hypothesis testing, confidence intervals. So what does this look like today? So we looked at the sample means when we knew the population variances, and then last class we looked at sample proportions. Right? So just to kind of remind ourselves what we were doing. Write this all out and then we'll kind of talk about it here, but here was what we were doing with our confidence intervals. We were just basing our confidence interval around that sample difference, adding a certain number of standard deviations to their upper bound, subtracting a certain number of standard deviations at the lower bound, and then, well, I need to go 2 standard deviations. How much is that? Well, it depends on what the standard deviation is. So we said the standard deviation of our sample means we would just add the variance of each group and then take the square root of it. So today, we're going to look at a more practical kind of example, which is I don't have my population variances, but I've got 2 samples, so I can calculate my sample variances. And kind of adding those together will represent, and then taking the square root would represent the standard deviation of the difference in my sample means. The only problem is we said to calculate these sample variances, I'm dividing by n-1. And so they won't be standard normally distributed. They'll be coming from student t distribution. Okay. So, I mean, once you plug the values in here, nothing looks any different for our confidence intervals. Just to kind of think about what we're doing with our test statistic. I'll have something up here for comparison. So before we were taking that sample difference, subtracting our assumed true difference, which I said I'm always going to kind of keep at 0 there, the problems I asked you guys about. And then divide by the standard deviation of the statistic that I'm interested in, which is, the exact same thing as what I was using for my confidence interval up there. Okay. Everything's going to look exactly the same when we're doing test statistics for the difference in sample means when we only know the sample variance, right? It's just going to look like different notation because we're not using a known population variance anymore. We're using those sample variances, right? So hopefully we can kind of start to see like this is a similar process. Take the statistic you're interested in, subtract the assumed true value of that statistic, divide by the standard deviation. Okay. Just now we're going to be using S instead of sigma because we've only got sample variances. And because of that, we're going to have to use the student t distributions. Now it becomes a little bit tricky. So before, when we're using that student t, actually maybe I have this here. Yeah, there we go. Before, when I used the student t, my degrees of freedom was simply what? Remember how we found our degrees of freedom? Yeah, so it was just n-1, right? Our sample size -1. Kind of seems odd, but there's a reason why, I think someone, maybe it wasn't this, maybe it was my other section asked, well, why don't I just use the sample size? If I'm subtracting 1, like, why don't I just have the table show me the sample sizes and I can look it up? And the reason is because when we get to something like two population tests, what our degrees of freedom is actually going to be, right? How many degrees of freedom, all of them, is this really nasty formula, which I'm not going to make you guys use. Okay. So I'll show you what it looks like today in Excel. I've kind of got it already pre-programmed in there. If I ever ask you to do this on an Excel individual assignment, I'll kind of have that formula because it's difficult to make sure you're getting all the parentheses correct. I'll have it kind of in there for you and I'll kind of show you how that would operate. Now, the reason why we have to go through and do this is because we said the degrees of freedom was n-1, because if I divide by 9 instead of 10, that's a bigger difference than if I divide by 99 instead of 100, right? And so when I'm adding these two variances together, how far off each one of them will depend on their sample size. Well, we're not guaranteed our two samples have the same sample size, and so it's going to be some ratio of those two things. So kind of notice really what's in here, you just got the variance of your first group, variance of your second group sample mean, variance of your first group, variance of your second group sample mean. So this is really trying to kind of take some type of a ratio of how far off you were from each sample because you were just dividing by n-1. Okay. So, I mean, the long story short is we calculate degrees of freedom differently. This is the equation that will do it. But there's some things in Excel that prevent us from having to actually use this, right? So if I ask you a question to find my degrees of, I won't ask you a question to find the degrees of freedom. I'll be giving you assumed true degrees of freedom in the examples that we work through, okay? Or I'll calculate them for you. And on the exam, I would kind of give you that assumed true degrees of freedom as well. So the steps look no different than what we were doing before. It's just we're using sample variances in the student t distribution. And then finding the degrees of freedom is going to be a little more difficult. But it's really like the same steps that we were doing for one population, just with a few more moving parts. And this degrees of freedom is a little bit more tricky. But like I said, I'm going to make you guys punt on that and not have to really deal with that issue. So we'll work through an example, and then we'll do some hypothesis testing, and then I'll kind of show you a little bit of stuff in Excel. So let's say I have texters and non-texters. So text is texters and T is non-texters, right? So I've got their response times, and I also calculated the variance in those response times for what, 49 and 64 drivers. So really at this point, all I'm going to do in a problem like this is if I want to build a 90% confidence interval for that true difference in response time is between texters and non-texters. Actually, I might have said that backwards, between non-texters and texters, the way I have it set up here. Well, I've got my two sample means. I've got my two sample variances, got my two sample sizes. It's going to be a matter of plugging those values into that confidence interval equation. So if I look at this, got what? The non-texters are a little bit more responsive, right? I look here, this is what? 0.16 and 1.44, 49, 64. So if I'm thinking about the possible values for, my confidence interval, I know that it should be centered around what value, approximately. I'm looking at this. So remember, what are we doing with confidence intervals? We're trying to find out upper and lower bound based off of the sample evidence that we found, right? So my confidence interval should be centered around whatever that true difference is that I found. Just like with one population, it was centered around whatever sample mean I found or whatever sample proportion. Well, now it's just centered around the difference I found in those sample means. So here it should be what? About -1 should be like the center of my confidence interval. So I found sample evidence that if this difference found it was -1 or less than 0. So what's that kind of telling me? I found evidence that texters are taking longer to respond while driving, right? Because in order for this to be negative, my second group would have to have a larger mean. So I found evidence that the people texting while driving were responding with longer response times, which generally is a bad thing, right? That means you run into the person in front of you, okay? So I found that, but it could very well be that the true difference was 0, and I just so happened to see we found negative, didn't we? A sample mean difference somewhere over here, right? So if my confidence interval, I'm going to build that. If that goes past that point of 0, well, then I can't really say that there is a difference between these two groups, right? Because one of the true values could be the difference is 0. The only way the difference is 0 is if they have the exact same response time. So if I find that there's only negative values in my confidence interval range, that's telling me that this true difference with 90% confidence, I could say that it's negative or that texters are responding with a longer period of time or response times are longer. Right? I know that I won't find that it's only positive because why? Yeah, my difference is negative. So if I'm building it around there, the sample difference I found has to be in my confidence interval. My confidence interval is negative. I know that I couldn't only have positive values. So we already kind of have two. We kind of know two of it's going to be one of the two outcomes. Kind of rule out that third. But really, at that point, it's just a matter of identifying what the problem gave you. Right. The only thing left we really have to look up is this student t value. Now we want it to be the value that gives us alpha over 2 on each side of our confidence interval. So if our alpha, well, our 90% confidence interval, alpha should be 0.1, which means there's half of alpha on each side of the confidence interval, or 0.05. And this is where, well, what's my degrees of freedom? I'm going to have to use this nasty formula. Right? Now, if I ever get a decimal, notice when we're looking at that student t table, my degrees of freedom has to be an integer value. So we always kind of said, so what we end up doing is if I have a decimal value here, I always just push it down, right? Or I'm going to a lower degrees of freedom to err on the side of caution, okay? Notice that I would go to a larger degrees of freedom, I'd be approaching that standard normal. So we'll just assume that we were at the lower value to kind of err on the side of caution, that we were, further away from it at the degrees of freedom of 80, even though the actual technical degrees of freedom would be 80.39. It's just that when we actually identify these student t distributions, they're only student t distributions for integer values. So I found 80.39. I kind of pushed that down to the next lowest degrees of freedom of 80. I wanted half of alpha, so 0.05 in each of my tails. Oops, spoiled my meme here. So we wanted 0.05, right? So we're in this column, all the way down to the degrees of freedom of 80. So 1.664, that was the last piece of information that we needed. Now it's just a matter of getting this plugged into our calculator. Okay. Any questions how I found that value or kind of anything along those steps? Okay with this for now. So, oops. Maybe, there we go. So now that we've got that t value, now it's just a matter of getting everything plugged in. Okay. So we get this range of negative 1.3 to negative 0.79. So we're thinking about negative 0.79 and negative 1.33. So the only values in my confidence interval negative. So with 90% confidence, I could say that this true difference is less than 0, or that my texters must have had a higher average response time than my non-texters, right? Which intuitively makes sense, right? And none of us should text while driving, and I'm sure all of us have. So this is kind of how you would approach kind of a confidence interval question. You've got difference in sample means, but only sample variances. And like I said, I'm not going to make you maybe compute these degrees of freedom. I'll kind of give you those assumed degrees of freedom. Okay. So like if I asked you this problem, it would have been set up where I gave you all the same information, but I told you assume the degrees of freedom is 80. I would tell you that. Okay. We're not going to do another confidence interval one because I think it's more valuable if we see how we do this in Excel. So we'll go through some hypothesis testing stuff, and then I'll kind of show you some of the tricks in Excel or some nice things that prevent us from having to do a lot of this work by hand. So the steps for doing hypothesis testing, when we've got the difference in sample means, but only sample variances, nothing's changed. I shouldn't say nothing. The steps haven't changed. The only thing that's changed is when I'm calculating my test statistic, it no longer comes from a standard normal distribution or the Z tables. It's coming from a student t distribution. So instead of a Z statistic, you might call this a T statistic, right? Just identifying it's a test statistic coming from the student t distributions as opposed to a Z statistic, which is a test statistic coming from the standard normal distributions. Okay. But once we have that, all the principles apply, right? If the p-value is less than alpha, we can reject. If my test statistic is larger than the critical value, in absolute terms, I can reject. And nothing else has really changed. So if we think about problem here, back later. Let's say I've got kind of two groups, and this one I kind of kept easy. The sample sizes are the same. but I've got 41 male, 41 female physicians. I've got the sample mean that I calculate from each group, and then I calculate the sample variance, right? So maybe I'm interested in something like, is there a gender pay gap or gender discrimination going on in terms of physician salaries? So if I want to test for whether or not the difference between male and female salaries is, whether male doctors earn different salaries than female doctors. So I got this term different than. What am I really thinking about doing with my null and alternative hypothesis? If I want to know that male and female physicians have different starting salaries, that's what I want to test for. Then I'm really saying that that difference would be, yeah, not equal to 0, right? If they're different from each other, then the difference between them will be some other value than 0. That's what I would think is probably happening, right? I probably think that there's a difference in gender pay here. So that's what I want to find. So I'll assume the opposite is true, which is that pay is exactly the same, right? That difference is in fact exactly equal to 0. Okay. Now, I've got a not equal to sign in the alternative hypothesis here. What type of test do I have? Two-tail, yeah. So what I'll think about doing before I can think about this, but before I even start plotting things, that if I find that this difference is, how did I set this up? So I want the difference between male and female. So let's say I find this positive test statistic. I can find the area to the right, but I have to remember it would have been equally as likely for me to see sample evidence I went against the null on the other side. So I'll need to multiply it by 2. Okay. So what would my critical values be here? And then we can kind of calculate our test statistic, plot our test statistic against those critical values. Well, here I'm just doing a critical value for one significance level, which is the 1%. Okay. So I've got a two-tailed test. How do I find my critical values? Well, I'm looking at this student T distribution. For a two-tailed test, I'm actually going to have a pair of critical values, right? Because evidence that's a certain number of, remember, you can think of our critical values as like the threshold number of standard deviations away. If our sample evidence ever gets this many standard deviations away from what we assume to be true, it probably isn't true. So we've kind of got our rejection region here. And if my alpha is 0.01, right? I'm doing this at the 1% significance or 99% confidence level. I'm going to have half of alpha in each tail or 0.005. Okay. And once again, we're just going to use that degree of freedom. If I plugged everything in to that equation, assume that it spits back out at me 80. In fact, I don't know. I'll mention it. It's a little bit unique. It's not necessarily I'm going to have to be done on it, but if I have sample sizes that are exactly the same, it actually kind of goes to this intuitive way to find degrees of freedom, which is I could simply add up my two sample sizes and subtract 2 now, right? Because I've got two samples. So notice here, 41 plus 41, 82 minus 2 would actually be 80. Right? And that equation would spit out you exactly 80 if you had the exact same sample size. Now, the sample sizes vary. Now that's where we kind of get some of these weirder degrees of freedom that might not look like integers. Okay. So what do? Well, only got sample variances. First of all, I can rule out C right away because I know I've got a pair of critical values for a two-tailed test. I go to my student T tables. We've got what? 0.005 was the area I wanted in the tail. I go down to that degrees of freedom of 80, 2.639. So I'm just going to plot those just to give myself a nice visual of where those critical values are and where my rejection region is. Now, I said the other way we could think about rejecting is if the absolute value of my test statistic, which is now a T statistic, is greater than the absolute value of those critical values, then I'm okay rejecting. Okay. So we'll go back here. The other thing that we now need is, well, what's our test statistic, right? I mean, at this point, it's just going to be a matter of plugging in our values, right? We've got 174, 141,000. The assumed true difference. Like I said, I'll always kind of keep this in these examples as 0, right? That kind of simplifies it a little bit. And then plugging in those large sample variances of 49.36 million, sample sizes of 41. It's really calculating these test statistics is just a measure of kind of getting these entered into our calculator correctly. And maybe identifying the correct test statistic equation is because I've got sample variances, right? So I can look for those S squared, right? Now, right away, I know which of these can't be my test statistic. There's something interesting that I mentioned that makes the test statistics a little easier when we have this assumed true difference of 0 and we're looking at the difference in sample means or sample proportions. The denominator of my test statistic is always a standard deviation. So it has to be positive. If I'm subtracting 0, then the sign of my test statistic is really just dictated by whatever that sample difference I found was. And that makes sense. If I found a sample difference that's negative, my test statistic is telling me I'm this many standard deviations below the assumed true value. Right? So I look here, right, if I phrase this as male minus female positions, I think that's how I did that. Let me double check on this. Yeah, so that's how I would have phrased it, right? So male minus female positions, starting salaries. I found a sample difference of what, 33,000, right? So I found a positive difference. So I know my test statistic is going to be positive, right? Now to actually find out what the answer is, whoops, I'm gonna have to plug everything in, right? And I get this wild test statistic, right? Almost 23. And so I think some of you ran into this problem when you're looking at the last Excel assignment. I got a huge test statistic and a p-value of 0. But sometimes that's the answer, right? So here, oh, I guess I can kind of show you here. I found a very large discrepancy between male and female starting salaries. So it's not that surprising that I'm way, 23 standard deviations away from the assumed true difference of 0. Probably here, a more interesting thing would be to say, okay, I know, like if I don't know this, well, I do know this, but you may not know it, right? But if you look at like overall male, female starting salaries in most occupations, right, you tend to see that males earn a higher amount, right? Now that varies across some, but we probably know going into this, we're going to find this positive difference. In fact, we may already know that, yeah, we have tons of old evidence that we can say that this difference is not 0. So what might be more interesting? Well, is that gap different than 20,000, right? Is the gap in between male and female starting salaries more than $20,000 or different than $20,000? Well, then things change a little bit, right? Because I now no longer am subtracting 0. I've got to subtract the assumed true difference of 20,000. And I'm not making you guys do that on the exam or anything, but in practice, you would want to do something like that, right? If you have a situation where you probably know, in this case, that male starting salaries are higher than female, well, you might want to know how large is that gap, right? I want to maybe be able to put a number to it, right? Can I say that it's more than 20,000 or more than 30,000 in this case? And those are, I guess, a little bit more practical, right? Of testing against values other than 0, even though, sometimes all we want to know is, are males making more than females in this specific industry, right? Because that's not necessarily always the case, right? There's certain industries where females actually make more than males, right? But going into it, if I already kind of had an idea of what that difference is in whatever industry here, physicians, maybe I want to use a value other than 0. And I can do that, right? Complicates it a little bit, but not too much. Is that making sense when I'm standing there? Any questions on that? So where's that test statistic? Way over here, right? Very clearly in my rejection region, even at that 99% confidence or that 1% significance level. So here I found evidence that I could very easily reject the null with. Once again, if that absolute value of my test statistic is larger than the absolute value of my critical value, I'll also reject, right? So I can draw out the visual, or I can kind of remember, this guy here. Okay. Now, if I want to do the p-value approach, I would have to find the area to the left of 23. Got a two-tailed test, so I would then have to multiply it by 2. If you had to take a guess, what's that going to be pretty close to? Yeah, 0, right? If I'm 23 standard deviations away, when we get to like 3 or 4, the area in the tail is already like below 0.01. So this is going to be something pretty close to 0. Something close to 0 times 2 is still really close to 0. we only reject if that p-value is less than alpha. So if my p-value is approximately 0, I'm going to be able to reject it like whatever level I want, 99.99%, right? And the test statistic's the same idea. This test statistic's so large that even if I only want, you know, half of 0.0001 in the tail, my p-value is probably still going to be, or sorry, my critical value is probably still going to be less than what that test statistic is. So both ways kind of give me evidence that I found extreme evidence that the assumed true difference of 0 isn't in fact the true difference.
This might be a dumb question, but is this like process like testing, like how they like can say it kills 99.9% of your
Related, right? So I'm going to show my naiveness in that field, but my guess is what they do is they take measures of how many, they probably start out with a certain amount of bacteria, they treat it, however many, or they then measure however many are left, right? They probably do that several times. So like each time is like an observation. They then look at the average number of bacteria left. And then actually, they don't look at, it's probably not a sample mean, it's probably a sample proportion, right? The proportion of that bacteria that was left. They then can say, okay, can I say that the amount left is, depends how you want to phrase it, but they could say, is the amount left less than 1, right? Because I know if there's less than 1 out of the 100 original bacteria that I've actually killed 99%. So I guess they would want what? 1,000 original bacteria and then test to see, can I say that the average remaining was 1? If I can say that, right, I can reject the null, then yeah, I can put that out in my ads and I'm feeling pretty confident about it. But it's not the same as like being able to say it. I guess in a way they can say with 99% confidence that they killed 99.9% of bacteria. But yeah, that's probably my guess is what most of these companies have to at some point do if they're worried about liability, right? Saying something that isn't true, they want to be able to have some type of statistical evidence that supports like, no, this is, you know, we thought at the 99% level this was true, and so kind of they can avoid maybe, you know, certain lawsuits with the imagination. Did that kind of answer your question?
Yeah.
Well, no, it's good. You should be curious about the world, right? So, yeah, but you could do things like that. If you think about when they say, oh, what's another good example? So a lot of the times you'll hear people if they make claims about like salary differences or whether or not there's differences across states, like you really should be doing the same sort of process, right? Now they may not say it to you. I can tell you with 99% confidence, right? They're probably just telling you that this group is larger than the other, but they should have some type of support from what we call a t-test, right? I'm going to show you that in Excel here in just a second, but this is a t-test, right? We're testing for differences in two groups. Right? Any other questions on this before we keep moving here? So, come back to matched pairs. I put this up on Canvas, so two population blank. I'll go through this really quick because the stuff I'll go through quick is not things that is, I don't know, either I think it's probably easy at this point or stuff that we've already done. So I'll kind of show you first. Let's look at, I think I separated that traffic stop data out into white and non-white drivers, right? So maybe I'm interested in something like, is the average age, right, that someone's pulled over vary across race? And, you know, this might seem trivial, but, you know, if the probability a ticket is issued to a younger driver makes more sense, like maybe they're pulling over younger non-white drivers as opposed to kind of white drivers, making it that, you know, individuals that are non-white are more likely to get tickets because they're younger and, you know, can have these negative implications. So maybe we want to test for that. Like we're interested, right? So I separated the data up just because it makes it a little bit easier. Otherwise, we'd have to introduce some additional formulas that I don't think we want to deal with. Okay. So what I'm going to do is pretty simple. I'm going to use these functions we've used before. So average var.s. And then count, right? So these are hopefully three that we're getting really familiar using. And I'm just kind of using that control shift, command shift, hit the down arrow shortcut to select the whole variable pretty quick. So average, var.s, count, that should give me the mean, the variance, and the standard deviation, or sorry, the sample size. Okay. So there's the count function, var.s, we selected the range, and then average, okay? So I'm gonna go over here and show you kind of a nice little trick. In fact, you don't have to do this, but I'm gonna copy this just so we can see what I'm doing here. So I can do this one of two ways, okay? I could calculate the average starting age over here for my white drivers on this different data set, control shift, hit the down arrow. And then because I have that over here, right, I'll do the variance as well. Sorry, before I show you this, I'll just do all three. So the variance of driver's age, and then use that count function to find the sample size. Okay. It should be stuff that we're getting pretty familiar with. Okay. Well, the problem is I've now got this data on this other sheet, right? And I've got my white sample mean, the variance in the white driver's age sample mean, and the sample size on one sheet, and then the same three statistics for the non-white group on another sheet. Right? So how can I get these on the same sheet? If I put an equal sign, I then click on a different sheet. Notice I can't see it, but this formula bar tells me it actually is using, so we not only can reference rows and columns, we can reference the worksheet that something's on. So notice here, this is referencing that it's going to the worksheet named white. And then once you're on that worksheet, take the value in cell Q2, and it should put it on my other worksheet with the non-white data. So once again, a nice easy way to kind of end this instead of like using arrows and accidentally selecting it, just hit enter, and it'll send you right back to that cell. So notice it took that value that was in cell Q2 on the white data sheet, and it put it over here. Okay. Does that make sense? Any questions on that? So this is, well, here, I'll copy this down because the way I had it set up, oh yeah, here's my sample variance, my sample size. When I copy this down, it keeps the worksheet the same, but it's updating those row and column references. Okay. Any questions on any of that? I want to see any of that again. So there's two things I want to point out now. I already had that really nasty formula already in Excel so that we didn't have to waste time and look, I mean, there's a lot of parentheses. I could have, made a mistake. So because I have this set up to have my two groups side by side, I knew that once I found the sample variances and the sample sizes, this formula would use those values and spit back out at me the degrees of freedom. Now, once again, I can't use degrees of freedom where there's a decimal, right? But I can do it if it's an integer, right? It's got a little lightheaded, but I think I'll be all right if I drink water. So we've got this degrees of freedom, right? We can now start using that to do things like hypothesis testing and confidence intervals, right? So I'm not going to go through and kind of set all this up. We've done confidence intervals with one population. It's the exact same for two. It's just that we have more moving parts, right? But to find that t value, we would do it exactly the same way, right? So I'm going to skip confidence intervals for now and look at instead hypothesis testing. So let's do the assumed true difference of 0, right? I'll kind of start out with that and then show you what if we wanted to do something other than 0. So I first need to find my test statistic. Once again, there's not a nice, easy way built into Excel. I'll show you one way to avoid this in a second. But here, I'm just going to have to use Excel to be my calculator. This was kind of like what we did for one population, right? So I'll go up here. Excuse me. I'll take my, I'll do kind of define this as a difference between the white and non-white group. So sample mean from group 1 minus the sample mean from group 2. Oops. I want to be able to show this to you. This is why working on a laptop is never fun, right? Now, I'm going to subtract the assumed true difference. Now, don't really have to do this because it's 0, but I'm setting this up just in case I want to test against a value other than 0. I would then divide by the square root of each group's sample variance divided by their sample size. Now notice it's putting up there in the formula bar. If I want to double check, scroll down. Oh yeah, sample variance over the sample size, and then add to that the other group's sample variance divided by its sample size. Oops. Jeez. 1 second. There we go. So really just using Excel to be my calculator to find my test statistic. I can then use Excel to find p-values and critical values to make my rejection decisions. Okay. Just kind of clear what I'm setting up this. And I'll put up the complete version of the file as well. So if I'm going through this a little bit too quick, you'll have kind of what this looks like. But it's really the same setup as what we're doing for one population examples, just a few more moving parts now. Okay. So I get a pretty large test statistic here. Right. So one thing I could do, I've got a text box in here, so I'll use my arrows, is find my critical value. So if I've got this set up as a two-tailed test, once I find my test statistics, similar to the problem we worked through earlier, I want the area in that right tail, and then I need to multiply it by 2. So I could, I think I showed you these before, use a little bit of a shortcut, which is t.dist, right? I'm using that student t distribution, and I've got a two-tailed test. So dot 2t. Now I could use the regular t.dist. It would give me the area to the left. I'd have to subtract it from 1 to get the area to that upper right tail, then multiply it by 2. The t.dist.2t will do all that for me, right? We said there was one issue with using it though. Remember what it was?
You
Can't have negative test statistics. I don't here, so I don't have to worry about it. But even if I did, I could still use it. And I would just be using that absolute value, right? Because it's a symmetric distribution, so it shouldn't matter if it's a two-tailed test. So I select my test statistic, comma, well, what's my degrees of freedom? I actually had that calculated up here already. Okay. So I've now got this two-tailed test, and I think I had this set up. This might be under the wrong thing. This is my p-value, right? I might have put this under the critical value title. I can't remember. So this is going to find my p-value, right? Oh, what did I do wrong here? Close my parenthesis. There we go. So let me move this over since that was actually my p-value, right? So t.dist.2t. You don't have to use the absolute value here, right? I'm just using it to be complete in case we did have a negative test statistic. But, you know, the only way that this .2t function works is if I tell it the positive value, and then comma, we already calculated that degrees of freedom with that nasty formula up there. Okay. Yeah.
Can you go back to, can you pull up the, yes.
Yep. So like I said, if it's easier, you can leave out that assumed true difference since it's just going to be 0. I'm just going to do that so I can show you something here in a little bit. Any other questions before we keep moving here? Want to see another cell again, or okay. So how can I find critical values? Well, my critical value is going to be the value that gives me what for a two-tailed test, alpha over 2 in the tail. So here, I don't know if I have this set up. It looks like I have it over here. Alpha, well, no, I didn't define it. I must have forgotten to do that. Well, let's do it at the very highest level. Let's just assume that we want to do this test at the 99% confidence level or with a 1% significance, making alpha 0.01, right? So here, I'm working in the reverse. I know the area I want in the tail is 0.01 divided by 2, comma, my degrees of freedom is up here, right? And this should give me that t-value, that critical value, the threshold number of standard deviations away, that where if I see a test statistic any more extreme than that, I'm okay rejecting. Right? So I hit enter. Now I have to remember, I can use that absolute value function, that I've actually got a pair of critical values, right? It's a two-tailed test, so same value, but one's negative, one's positive. Now, this one pretty easily, that test statistic is so large, I'm clearly going to be in my rejection region. Kind of like the one we just worked through. Okay? And my p-value is basically, right, e to the negative 141, that's 0, right? In fact, you know, I don't even know why it, you know, I'm surprised it doesn't show us that it's 0, right? There is a limit to how many, kind of what that negative value will be here that'll display to you. So we could go through, we could use that if statement to make our rejection decisions again. I'm not going to kind of waste time with that. We could just look at this and then kind of determine, oh, yeah, clearly we can reject with this, right? Now, one thing that's interesting is I don't have to just test against 0, right? So if I have this set up, I could actually think about this as, well, can I say, so what I'm saying here is I started out with a two-tailed test, assuming the difference is 0. I can reject that. So I can reject that the average age of white and non-white drivers is the same, right? It's different, right? In fact, if I wanted to do a one-tailed test here, I can actually say that the police are pulling over much younger non-white drivers, right? That probably not only is that this difference something other than 0, but that it's in fact negative, right? Based off of the sample evidence I found. So I would have to change things if this is a one-tailed test, but pretty clearly here I found evidence that, you know, something systematic in how police are pulling people over, they're pulling over younger non-white drivers. You know, not to get into a lengthy discussion of racism in America and things, but I imagine you can like, imagine these stories, right? And so this is pretty compelling evidence. I mean, we have a really large data set, which helps, right? We have this huge degrees of freedom because our sample sizes were like in the tens of thousands, but big data is like, I mean, you guys are in the business college, like big data, you know, is a big thing, right? And so all these, there's data on everything out there now. We can make a lot of statements really easily because our data sets are going to be so large, right? It's going to drive down that standard deviation, making the test statistics really large, p-values really small, which make it more likely we can reject the null. So here I found pretty strong evidence that these average ages of these two, you know, white versus non-white drivers is not the same. In fact, I could probably say, is it different than, I don't know, 2 years, right? Are they a whole 2 years like younger? P-value is still pretty close to 0, right? Well, can I say it's different than 3? Man, I can say it's different than 3, right? So I can really start to pinpoint down like how severe of a problem is this? Not only can I say, are they different, but the difference is more than 3 years of average age, right? That tells me that the police are probably systematically doing something very different when they're pulling over non-white drivers as opposed to white drivers. Is that any questions on that? Is that hopefully we're seeing like this, these are like powerful statements. Like these are very like, you know, policy, you could suggest policies, you know, after this. But I'm going to set this back at 0 for a second because I want to show you something else. So this is a pain, right? This is not fun. I don't like entering all that into Excel. You know, I know I'm just using Excel to be a calculator, but is there something programmed that will do it for me? There's actually this shortcut, and I show it to you how to do it this way because it's kind of how you would do it by hand. It kind of breaks it down to conceptually think about it. What we'll start moving towards on Friday, and then for the rest of the classes, we're going to be doing like black box stuff. Like we're going to tell Excel some stuff. It's going to do a lot of work behind the scenes and then just spit an answer out of us. So this T-dot test kind of black boxes this process, right? You don't know what's in the box, something's happening, and then it spits out at you an answer. So what I can do with this T-dot test is select my first group. So this was actually, my first group was my white drivers. So I go to that worksheet, Control Shift, hit the down arrow. Now I go, whoops, that's not what I wanted. Let's see. Right. I'll go up here to this formula bar, put a comma, and then going to go to my non-white worksheet. Now notice when I click on these worksheets, it automatically puts that name in there. I don't really need that anymore because I'm back on that non-white worksheet. I can leave it in there if I want, or I could delete it and then just select the variable for my second group. So their drivers, you know, non-white driver's age. So all I've done there, if I can show this to you, is go to that white sheet, select that variable of driver's age, go to the other sheet, select non-white, select that driver's age, right? Now, if this all had been kind of side by side, that might have been a little bit easier. I could have copy and pasted these, but this was the original data. So this is one way of doing it. So I've now got my 2 columns of data. comma, I tell it how many tails is this type of test? Two-tailed test, right? And then comma, there's three different options that this form or this built-in function t dot test can do. One is going to be a matched pairs, which we'll talk about that on Friday. The other one would be if I've got two sample means that have equal variances or two sample means with unequal variances. Well, for us, and more often than not, the second situation is very unlikely, right? It might be if I was like taking two samples from the same group, so I know they should still have the same variant, like population variance, even though I can't see it. But it's not very, very practical. But that is one of the options they have. So we're never going to use that option two. We'll look at matched pairs with this t-dot test. And then we'll also look at when we have two samples, two sample means, but we've got different variances, right? And if we go scroll up here, we can see the sample variances weren't the same, right? I mean, the probability that they're exactly the same is in fact 0, right? That they're the exact same decimal value. So that really 3 is the only option that makes a lot of sense for us. So we'll put a 3 in here, okay? So that fourth thing is identifying what type of problem you have. We've got sample means and different sample variances, unequal. So what this will do behind the scenes is take these two columns of data, just like we did, calculate each group's sample mean, sample variance, and sample size, right? It's then going to take those, calculate the test statistic. You can't see it, but it's doing that. It's then going to take that test statistic, find the p-value, depending on if it's a one or a two-tailed test, right? If it's a two, you tell it it's a two-tailed test, it'll find the area in the tail, multiply it by 2. It's a one-tailed test, it just finds the area in the tail. And then it spits back out at you the p-value, right? That's what the p-value is, that area in the tail, and then we multiply it by 2. So it does all the work, but we just can't see it. So hopefully, if I told you, if this is correct, I should get the same values I have up here. Sure enough, it's off, maybe round a little bit differently because I kind of broke this down to intermediate steps here. But I think the built-in function, so like, notice here my test statistic, Excel just has that stored. When the t-dot test does it, it does truncate it out to like 100th decimal or something. So you can get something that's off. I mean, we're off here at the what, 138th decimal, right? So we're getting really, really precise with that t-dot test, but saving ourselves a lot of time. Okay. Questions on that? So hopefully we kind of see that t-dot test could save us a hell of a lot of time. One of the issues with this is though, it's only for these kind of student t distribution values. Now it doesn't, like if we had known population variances, right? It can't take known population variances. It would still calculate the variance from the samples that you have. So we can't really do the other two types or proportions. We can't really do those types of examples with that t-dot test. But for our sample means where we've got different sample variances, then we're okay. Any questions? I see something again. Just about out of time here. And I'll also show you one other thing. So why did I break it down? Show you the other way to do it. If t-dot test is so much easier, right? Well, the only other problem, and once again, I don't know why they don't add it like a fifth thing you can tell it, which is that t-dot test always uses the assumed true difference of 0. So notice if I want to do something like 3, now they're still really small, but right, they're going to be way different, right? Because that t-dot test only ever uses that assumed true difference of 0. So in practice, if we want to make statements about the gap being a certain magnitude, right, not just that they are different, but that the difference is more than 3 or something other than 3, we couldn't actually use that shortcut, right? Unfortunately. Okay. Questions? Keep moving here. So I'll put up a more complete version of this. I'll have the confidence interval stuff in there. I'll also put up kind of how you would do this step by step with proportions. Obviously, we won't have that t-dot test shortcut there, but we could, basically use Excel to be our calculator to find the test statistic. The principles behind finding the p-value, critical values would be exactly the same as what we're doing with one population. Just that test statistic equation, there's a little bit more kind of math you have to have Excel to for you, right? Just a little bit longer of an equation. So we'll do something a little bit different on Friday, which is matched pairs. I'll kind of introduce the idea, talk through some examples, show it to you in Excel. And I think we should have enough time to start something called ANOVA testing, which is kind of leading us into regression, right? Which is what we'll kind of continue for the next couple of weeks until the semester's over. Okay. All right. I will see you guys on Friday.